Okay, greetings, Mr. Abdul Muiz. My name is Jessalyne Desiree, and I'm from the international program of the electrical engineering major. And today I will present you my final project for the subject embedded systems, which is a DIY digital seismograph. So, what is the problem that I'm trying to bring to light? Which is It's an earthquake, basically. So an earthquake is a sudden and violent shaking of the ground caused by movements of tectonic plates. This is a very big problem, especially when it occurs, because earthquakes can cause millions of casualties. One of the most notable earthquakes being the 2004 Aceh earthquake, which has taken up millions of lives, and the 5.6 scala Richter Cianjur earthquake in 2022, which even though it didn't take up as much lives, it's still devastating. So the solution to be able to predict when an earthquake, to be able to predict or detect when an earthquake is happening is with a seismograph. So anyways, a seismometer is an instrument that responds to ground displacement. But combine that with a timing and recording device, and we have a seismograph. So the components of my DIY digital seismograph would be four of these main components. First of all, we have a microcontroller, which is an Arduino Uno that I'm using. And then we have the sensor, which is an MPU 6050 sensor. And then we have the buzzer, LED and LCD to display warning or signs that an earthquake is happening based on varying intensities. And then the breadboard and cables, which is to connect each of the components. So how does it work? First of all, the system is placed on a table or a stable ground and then shaken with varying intensity. Now, this intensity is so that the MPU 6050 can read different kinds of intensity. And to signify the types of movements, an LCD will display a warning and a buzzer and LED will also turn on. So for example, if it's mild movements, the LCD will display mild earthquake detected, and the buzzer and LED will buzz and bleep for once every second. And for medium intensity movements, the buzzer and LED will buzz for twice in each second. And for severe earthquakes or severe movements, the buzzer and LED will buzz 4 times in each second. Next, the data is then logged and displayed in the serial monitor from the Arduino IDE. And to save the data in a TXT and CSV file in which we can process the data later and get the graph, we can use the CoolTerm software. So this is the system architecture. As you can see, the LED, first of all, we'll start from the LED. So the cathode of the LED will be connected to a resistor and then connected to a ground. And then the anode will be connected to the 13th digital pin of the Arduino. And then this is a buzzer, and the negative side of the buzzer will be connected straight to the ground, and the positive side will be connected to the 12th digital pin of the Arduino. And then this one is the MPU 6050 sensor. So MPUs and LCDs, they communicate with the I2C protocol, which is also known as inter-integrated circuit protocol. So basically, it's a kind of protocol that allows multi-master and multi-slave devices to communicate with each other only using two ports, which is SCL and SDA. So the SCL pins of both the sensor and the LCD will be connected to the A5 pin of the Arduino Uno, which corresponds to SCL in the Arduino as well. And the SDA of both the sensor and the LCD will be connected to the A4 pin of Arduino Uno. All right, so what is MPU 6050 exactly? It is a complete six-axis motion tracking device. It combines a three-axis gyroscope, three-axis accelerometer, and digital motion processor, or DMP, all in a small package. So the gyroscope is basically to detect movements in X, Y, Z axis, so the rotational velocity of each axis. And the accelerometer is to detect inclination in X, Y, Z axis. So this is to detect the angle or the degree to which an object is moving, or we can say it as pitch, yaw, and roll. And the DMP is to compute motion processing algorithms. So what are the constraints of this? Even though this is highly feasible, because it's not that expensive, but the accuracy of the MPU sensor can be affected by environmental noise and external vibrations, which may introduce false positives or false negatives. And the second one is the system's reliance on the I2C protocol for communication between components introduces potential limitations in terms of data transfer rates and bus congestion, especially if multiple sensors are integrated. So, like I said, this might be feasible if the system is only like this, if the system is only as simple as this. But if you start to introduce more sensors, like let's say maybe temperature sensors to detect temperature, then maybe it won't be as reliable as this one is because of the I2C protocol. So with that, I will head straight to the simulation. Okay, so this is the simulation in Walkwe. So in this left side of the screen, we have the Arduino code. Yeah, I think this is self-explanatory, but let me explain a bit into details. So first of all, we need to define, we need to include the libraries, right? And then we need to define the components and also define the mild values, medium values, and severe values, because as I said, we will have three types of quote-unquote earthquakes, which is the mild earthquake, the medium-sized earthquake, and the severe earthquakes. And then in the setup function, we will have to set up everything. So we have the LCD, we set up the LCD, and then the serial begin. And then we set up like how the LCD will print the movements. And we have the data logging process, which is to display the time, the X, the Y, the Z axis, and the earthquake level. And then the loop function, first of all, we're gonna have to get some data from the sensor, and then we're gonna convert it to G-force, and then we're gonna count the total G, which is then later used for describing which kind of earthquake this is. So yeah, if total G is larger or equal to the severe value, then the earthquake level is 3, which is the most severe one. And if the total G is if the total G is less than the severe value but more than the medium value, then the earthquake level is 2, which is a medium-sized earthquake. And if the total G value is larger than the mild value but smaller than the medium value, then it's just an level 1 earthquake, which is a mild earthquake. And if there are no and if all the values are less than the mild value, then the earthquake level is 0. So essentially it's normal, or there is no earthquake. And this is the switch function, and this is the switch case, as said before. So if it's case 1, it's going to be a mild quake, and the blink and beep, which is later in here for the LED and the buzzer to notify the user. So if it's a mild earthquake, the LED and buzzer will buzz and beep for 1 second, once every 1 second. And then for a medium-sized earthquake, the LED and buzzer will buzz for twice in every second. And for the severe earthquake, the LED and buzzer will buzz for 4 times in each second. All right, and then the last one is for the data logging, which will be explained later. We can run the simulation now. All right, so we started off with a medium-sized quake. So in this simulation, we can carefully drag this. So if it's normal, like the LED won't do anything, right? And then if it's let me get it to a mild earthquake. Wait. Okay, the mild quake, the LED bleeps for once every second. And then in a medium quake, the LED will bleep faster, as it bleeps twice every second. And then for a severe quake, the LED will bleep faster because it bleeps for 4 times every second. And as we can see, this is the data right here. In this simulation, the data is just like this, but if it's on the Arduino IDE and the in real life situation, it might probably be different. And so that is all for me. But I will have an explanation of the next of the in real life circuit and the data logging process next. This is the in real life thing. All right, as you can see, the LED bleeps, but honestly, for some reason, I don't know why the buzzer is not buzzing. But it is showing like different changes of values, but it is stuck on severe quake and medium quake, but I don't know why there's no normal or mild quake. It's probably because of the sensitivity of the MPU 6050, but either ways, this is how I'm gonna log the data. So I'm using this thing called I'm using the software called CoolTerm XE. All right. So first of all, we're gonna identify like the serial port. and I'm using the COM5 for the Arduino. Okay, and then we connect it, and as this connects, this resets again, so that's cool. All right, and as we can see, the cool term is keeping track of the data. So let's vary the data. Okay, sorry, this might be a bit loud. I'm shaking this, shaking it like that. Okay, so thing that I noticed is that the status in here is different from the data being recorded in here, and it's probably because like this one is more real-time and in tune with the sensor, with the data that is being sensed by the sensor, and this one only counts per millisecond, per couple of milliseconds, yeah, per second. So this one might change for every half of a second, or like a time interval smaller than that. So yeah, afterwards we're gonna disconnect this, and then this is automatic, and then we can save this as like a text file. Okay, I'm gonna change the name a bit. As we can see, I already have like a file that contains like the same thing. Okay, and then afterwards we can like open the thing with Excel, and this is from my previous readings. Yes. All right, then that's about it. Thank you.